So, yes, thank you for the introduction. I'm sorry that I can't be with you in Montreal this week. I was hoping to come, but had to, in the end, stay at home to help with the childcare. And it's probably a good job that I did, because my daughter, my one-year-old daughter, had a stomach bug at the weekend. And if my wife had been left to change all 15 dirty nappies just on Sunday on her own, then I'd probably never have heard the end of it. But here I am. I'm going to be talking about a spatially dependent fragmentation process, and this is joint work with my former PhD student Alice, who's currently in Munich. And these pictures will appear later on in the talk, so you'll sort of see some explanation later. So the motivation for this project came from, well, the sort of traditional mathematical theory of fragmentation. So if you look in Bertoine's book, he gives some examples of processes that you might find in kind of real life that involve things breaking up into smaller and smaller pieces that want to model mathematically. He sort of says that if you want to deal with them mathematically, you need to make some assumptions. First of all, we suppose that the system has a memoryless property. And second, we assume that each fragment has some real number associated to it that we can think of as its size. That has to sort of characterize the whole fragment. So we can't sort of consider the spatial position or the shape of particles, thinking from the point of view of applications, or even just sort of trying to do things as general as possible mathematically. What I wanted to do was to relax this second assumption. So that the aim of this project was just to relax that assumption that we have to have one real number that characterizes each fragment. So the model that we actually came up with was inspired by the last of these applications mentioned at the top. So if you imagine a block, let's think about a sort of concrete slab, maybe. Oops, see if I can actually draw on here. A concrete slab being smashed into smaller and smaller pieces. You might expect that pieces that are long and thin, like this, are going to break much quicker than pieces of similar area, but which are almost square. And also that the long, thin pieces might be more likely to break along their longest side, like that. And according to the traditional theory of fragmentation processes, you couldn't do this. So our model sort of tries to represent this in a mathematical form, and the aim is to just come up with some model that's a sort of proof of concept that you can relax this second assumption and still get rigorous results. So here is the model. We start with a square with side length 1, and the square just splits at rate 1. So we're in continuous time. We have an exponential random variable of parameter 1, and when our exponential clock rings, this square splits into two pieces, two rectangles. It has probability of half of splitting horizontally and a half of splitting vertically. And once it's decided which way it's going to split, it chooses a uniform point along its base or its height and splits there. Okay, so there's our first split. But now we've got two rectangles, and each of these, given their current sort of shape, their current dimensions, they behave independently. But they split at different rates. So the long, thin one here is going to split faster than the one that's almost square. Okay, yep, so the splitting rates depend on the shape, and also rectangles are more likely to split along their longer side. Okay, so sort of carries on. There we have it, right? So that this longer, thinner rectangle was more likely to split first, and indeed that's what happened. And then the system just carries on evolving like this. Okay, and to finish defining the model, what I need to tell you is the splitting rate specifically, and the probability of splitting, say, vertically as opposed to horizontally. So what is a natural splitting rate? We want something that's 1 when you've got a square, and something that gets large when you have a long thin rectangle. So the first thing you might think of is sort of the ratio of the base divided by the height divided by base. But then if you think about this a little bit longer, you realize these quantities, the height and the base, are kind of behaving. So at each jump, at each split of a rectangle, one of these gets multiplied by a uniform random variable, which has mean 1/2. So these things are actually fluctuating. These ratios are actually fluctuating quite fast, and the rate function quickly gets kind of out of control if you try and use this. So it's much more sensible instead of to turn this multiplicative behavior of these quantities into additive behavior by taking logs. Okay, so we change it to looking at log of height, log of base. Okay, apologies for the handwriting. Okay, so that's basically what we do. There's the slight added complication that then, if we just had log of base divided by log of height, well, we start from base and height both being 1, so we then have 0 divided by 0, which is a bit inconvenient. So we stick on this extra 1. We look at 1 minus log of base and 1 minus log of height instead. Yeah, and that has the properties that we want, that it's 1 if we have a square, and it goes to infinity if as you get arbitrarily thin. And you know, I'm not expecting you to sort of memorize the exact form of R. It won't be that important. And while this is the one we used for our project, I don't see any reason why one couldn't do a more general class of splitting rates using the same methods or similar methods. Okay, and similar logic, you can come up with the natural probability of splitting vertically. Again, it looks kind of a bit complicated, but really it's a fairly natural thing. It's just this is going to be 1/2 when you've got a square, and so this is the probability of splitting vertically, so it's going to go to 0 as the base goes to 0 for a fixed height. So again, it's not really important the exact form of this, just that, you know, there is some probability of splitting vertically and some rate of splitting, and they depend on somehow the ratio between the base and the height. Okay, and if we do some simulations, here are some pictures. I might try and share the actual videos. Maybe I'll do that at the end because I'll have to stop sharing my screen and share a different window. But on the left here, you've got a homogeneous model. So here, just every rectangle splits at a constant rate 1 and has probability 1/2 of splitting vertically or horizontally. And you see you get lots of long, thin rectangles just through random fluctuations. Whereas the one on the picture on the right is our model, where we have these inhomogeneous splitting rates and inhomogeneous sort of splitting directions, and it leads to a much, I guess, more homogeneous picture, in that rectangles like to be squares in our model. They prefer to be squares. They sort of tend towards squares, so you don't get as many of these long, thin things. Okay, so how are we going to actually prove things in this model? Well, as you might guess, if you try and well, certainly if you know the fragmentation literature, if you take the rectangle's dimensions, so b for its base and h for its height, the natural thing to do is to look at minus log of those things, plot those as x and y, and then you have this alternative description as something like a branching random walk, where we start with one particle. We started with a square of side length 1, that corresponds, if we take logs, to being at 0 in R2. And because our rectangles, when they split, they can only get smaller. That corresponds to positive jumps. It corresponds to x and y getting bigger. So we're going to actually live on R2 plus. When we're at position xy, we branch at this rate r. And when we have a branching event, the particle, each particle is replaced, sorry, the particle that branches is replaced by two children, and they have this probability p of, so when these branching events happen, either both children jump horizontally or both children jump vertically. And the probability that they both jump horizontally is this p of x and y, depending on where the parent particle was. And if they choose to jump horizontally, then they jump to positions x minus log u and x minus log 1 minus u, keeping their y coordinate fixed. And similarly, if they choose to jump vertically, then they keep their x coordinate fixed and jump to y minus log u and y minus log 1 minus u. So, yeah, I sort of said this is like a branching random walk. It's not quite a branching random walk because each particle is not doing a random walk. Sort of where they jump to or the direction they jump in, and apologies if you can hear my children screaming in the background. The rate of jumping and the direction they jump in depends on their position. So it's not really a random walk. Maybe it'd be more accurate to describe it as a branching Markov chain with uncountable state space. But nevertheless, from force of habit, I'm going to refer to it as the branching random walk picture. And the question we want to answer is, well, how many, well, for the rectangles picture, sort of how many rectangles are there at a large time and what sort of shapes do they have? Shape in the rectangles picture corresponds to position in the branching random walk picture. So, so the question in the branching random walk picture is how many particles are there and where are they? And this is definitely not a simple question to answer. You can, sort of to see why, you can think about a phase, you can draw a phase plot, particles x and y positions. So particles that are almost square are kind of just branching at rate 1. So you can imagine a line going along this lead diagonal, just branching at constant rate 1. But if you try and follow a different direction, maybe this direction, your ratio is bigger, so you start branching faster, but also your dragged particles like to be squares, so you're sort of dragged back in this direction. Okay, but maybe you're churning out enough particles that some of them can keep going in this direction and then get dragged back. And it's symmetric about the lead diagonal. So the same happens if you start going this direction, you start getting dragged back towards the lead diagonal. It's not clear, sort of, if you want to figure out where most of the particles are, it's not clear what tactic they should follow. And even if you fix a point, let's say it's a bit point Z here, if you want to know sort of how many particles are near Z some large time, how should they get there? What's the best way of getting there? What does a typical particle that finishes near Z do? Does it go in a straight line towards Z? Draw like that, or does it somehow follow this? Go branch faster by going like this, and then relax and head back towards Z. What we do is fix a function f. Instead of just looking at a point Z, fix a function f. So maybe f looks like this. And we want to know how many particles have paths that look like f. Okay, so now I want to work with a fixed function f, and I'm working with large times. I'm looking at large times. So what I'm going to do is rescale the paths of my particles so that they're functions on 0, 1, so that I can compare them with a fixed function f. Okay, so I need some notation to do that. I'm going to take a large time t, let nt be the set of particles at that time. And for a particle u, I let zu be the position of the unique ancestor of u in nt. Okay, so that just basically means the position of particle u at time t. And I'm going to rescale that linearly in space and time. So zut is now this linearly rescaled path of particle u. And what am I comparing these paths to? Well, I want my functions to be non-decreasing, as I said. So rectangles can only get smaller. That means jumps can only be positive. So I want non-decreasing Cadillac functions from 0, 1 to r plus, starting from 0. And of course, I'm going to actually look at e squared because I want because my particles are moving in 2 dimensions. So I take a subset of e squared, and I want to study nt of f, which is the number of particles whose t rescaled paths fall within f. I'm going to study that as t goes to infinity. That's the sort of the object that we're really interested in. And you can think of this set f as being a small ball around a fixed function, and you're really interested in how many particles look like that function. Okay, and if we rescale particles, then we also have to rescale these rates that we introduced. So this is going to be a bit of a technical slide. You don't really need to absorb it all, but I'll try and point out one or two interesting points. So it's quite easy to see that when you rescale the branching rate r, you basically just get rid of these plus ones. You end up with this function r star, except there's a bit of an issue near 0. So if x equals y equals 0, we fudge things, set this thing equal to 1, but notice that the r star is then not continuous. It's discontinuous at 0, which actually ends up causing quite a lot of problems later on. Similarly, the probability. So remember, we had the probability of splitting vertically. A vertical split reduces the size of your base. So it corresponds to a jump in the horizontal direction. So this was the probability of jumping horizontally. And when you introduce the rescaling, it looks slightly simpler. Again, you get rid of the plus ones, except that it becomes discontinuous at 0 again. And just for in the interests of being able to state a theorem, it helps to multiply these two things together to get the rate of branching in the horizontal direction, and multiply r star by 1 minus p star to get the rate of branching in the vertical direction. Okay, again, you don't really need to remember any of this. It's just letting you know that you can do this rescaling on these functions, and the only problem it causes is at 0. Okay, so to state our theorem, or to figure out what our theorem should be, just note that for a function f, for a Cadillac non-decreasing function f, we can write f as an absolutely continuous part plus a singular part. So you can think of f hat here as the jumps in f. So if f doesn't have any jumps, then f hat will be 0, and we don't have to worry about it. And we think about the many-to-one formula that Jason talked about mainly in lecture 2, I think, of his course, which basically says that the expected number of t rescaled particles that stay near f up to time little t should look like, well, if you fiddle about to rescale everything, it should look like, okay, you've got e to the integral of the branching. So this is the sort of reward you get from branching. And then you've got the cost of actually a typical particle having to follow near f. We want to figure out the cost of a typical particle following near f. It's a little bit complicated, but this is the formula that you get. I'll try and explain where this comes from. So if you just concentrate on this part here, so fix a time s, then we know that if a particle is near f of s, then it's, well, you might guess that it's jumping at this rate, jumping in the horizontal direction at this rate r star x. Except we saw in the many-to-one formula that the typical particle, for size biasing reasons, is actually jumping at double the rate, 2 r star x. So we've got particles jumping at instantaneous rate 2 r star x, and we want them to be jumping at rate f primed x in the x direction. And they're doing exponentially distributed jumps, so you sort of feed that into the large deviations, the standard large deviations formula, and this is what it spits out, this bracket squared as the cost of doing that. And we want to do that at every s between 0 and t, so we just integrate between 0 and t and hope that that gives us the right cost. And we also need to do the same thing in the y direction. So we add on the same thing in the y direction. Hidden assumption here is that those two things, because we're just adding them, that's sort of claiming that they happen independently. Now, jumps in the x and y direction are definitely not independent, in that at every jump we can only go either in the x direction or the y direction, and which one we choose is heavily affects what's going to happen in the future. But if we're just looking at an infinitesimal time s, then these jumps are happening as a Poisson process, at least roughly a Poisson process. So from that allows us, if we look at just a small amount of time, that allows us to get enough independence to sort of separate out these two, the horizontal and vertical jumps. Okay, so as I said, we sort of hope this is the right cost of following f up to t, except that we've forgotten that this doesn't take into account the jumps in f. So if f has discontinuities, then this is not the right answer. And to get the right answer, we have to look at the next level up in large deviations for when our jump distribution doesn't satisfy the strong Brumaire condition. And notice that I said that the jumps are exponentially distributed. That's why we have the discontinuities are possible. That's just because our splits were uniform random variables, and we took log, minus log of those. Minus log of a uniform is exponential. So we have exponential jump distribution in our random walk, or in our Markov chain. That leads to macroscopic discontinuities in the paths of particles. And that means we have to have this extra cost, the sum of all the jumps up to time t. So the true cost of following f up to time t is this j of f and t. Okay, so that's the cost. If we look back to the many-to-one formula, we have to sort of pump that cost up by the reward from r star, and we end up with k tilde, which is the integral of r star of f minus j of f. Okay, so that's like the reward minus the cost, and we might hope that this somehow characterizes how fast the system is growing. And indeed, if we plug this back into our many-to-one formula, this should look like e to the t k tilde of f and t. Okay, so it's all looking good. We can get these approximations working, but the problem is, if there exists a small t such that k tilde of f and t, let me change the color. So if this thing is negative, then e to the, well, t is getting large, we've then got e to the something negative times t. So this expectation is extremely small, and the probability that there exist any particles following near f up to time t is very small. And if there aren't any particles up to time t, then there won't be any particles up to time anything later than t. So certainly time 1. Okay, so k tilde is not quite the right thing to look at. Instead, we have to look at this thing k. So k tilde, so k is just k tilde. It's just k tilde if you stay, if k tilde stays positive all the way, and it's minus infinity if there's ever a time such that k tilde goes negative. So minus infinity corresponds to there not being any particles following the path. Okay. And there are some other sort of technical conditions in here that I won't go into, but that's the main takeaway message. If k tilde stays positive, then k equals k tilde. And if it ever goes negative, then k is minus infinity. And our theorem basically says that nt of f is approximately e to the t. Sorry, well, that doesn't make sense. E to the t sup over f little f in big F times k of little f. Okay. Again, apologies for the handwriting. Right, and the theorem is sort of written in this large deviations style, but it's very much not a large deviations result. In fact, it's about, it's an almost sure result. It's about events that happen with probability 1. So it says that this happens almost surely. Okay. So sort of theoretically, we've solved our problem, at least from my point of view as a probabilist, we've solved our problem in that we can say, if you give me a function f, I can tell you how many particles stay near the function f. But the problem is that taking this supremum, figuring out what this supremum is for a set of functions, capital F, figuring out what this supremum is, it's not so simple, and we haven't done it. So you might like to know, for example, what's the supremum over all functions of k of f, which corresponds to exactly how many particles there are. So if you think back to that phase plot that I drew for a fixed z, what's the supremum of k of f? So how many particles are there at z? What's the supremum of k of f such that f of 1 equals z? And for what values of z is there an f such that k of f is positive? That corresponds to what shapes rectangles can have, basically, or in other words, the boundary of that set would be where the extremal particles are. So it's not as simple as having a rightmost particle anymore because we're in 2 dimensions, but this is the sort of corresponding question. And in all these cases, you can ask, what does the maximizing f look like? And yeah, we haven't answered all these questions. We haven't answered any of these questions. Basically, Alice had to write up her PhD thesis, as we ran out of time. I would kind of like to look at them. I would like to know the answers at least. And it's possible that someone listening to this talk could tell me the answer very easily. I have no idea how difficult these questions are. Like I say, we didn't spend a long time thinking about them. So you know, if you think you can answer them, then please do let me know. Otherwise, you know, I'll have to think about them myself at some point. Okay, some brief words about the proof. How long have I got? Yeah. So as I hinted earlier, what we do is we break up time into tiny intervals, and on each small interval we know where f is, and we know its gradient. So we can, if we know particles are near f, then we can control how fast they're jumping in each direction. Okay, and yeah, so to be more specific, we can bound the largest and smallest values that our rate r can take when z is within when a particle is within a small ball around F, we take two compound Poisson processes, one with the maximum value of R and one with the minimum value of R within that range. And we use a coupling to trap our typical particle between these two compound Poisson processes. Okay, so yeah, we use a coupling to do this trapping, and then kind of things, at least the most broad brush version of the proof is that we then use first and second moment bounds to translate this behavior of the typical particle, which we can bound in this way into estimates for the whole branching system via many-to-one, many-to-two formulas. But there are some complications. The discontinuity of R star and P star at 0 means that the behavior is at early times is really hard to control. So I think Ofer drew this picture in his talk about where you want to draw your tree and cut it at some early level K and almost let it branch freely up to level K or time K, and then use this independence to help you to control the second moment calculations for the sort of bottom part of the tree here. But for us, the top part is really the most tricky part, because the top part is where there's these discontinuities in R and P. So we really have to, we really had to scratch our heads for quite a long time to manage this. And in the end, we came up with a discrete time argument where so it actually corresponds to, like I said, there are particles that behave like, or particles that remain close to square are branching at rate 1. So we can sort of guarantee using a discrete time argument that there will be some particles following this path at early times. And then we show that there are enough of these to sort of feed off into other directions, whatever other, whatever possible other directions there are. Somehow we can get good enough control in that way to get the argument working. Okay, yeah, so discrete time argument, show there is growth along the leading diagonal, and that these particles can feed growth in other directions. Okay, and another complication is that because we've got jumps that are exponentially distributed, this leads to macroscopic jumps. So even when we rescale particles, you still see really jumps of order big T, which means macroscopic jumps that are visible even when you've rescaled, even in the scaling limit. And that in particular means that we can't use the Skorohod J1 topology, the standard topology. The nice thing about our setting is that our functions are increasing, so we can actually use what's known as the Levy metric, which generates the Skorohod M2 topology. And actually this complication, once we figured out it was there, or once we figured out sort of what topology we should be using, that's not too much of a problem. Whereas this behavior at early times was really required some non-standard methods. Okay, thanks a lot for listening. I now have to try and figure out how to get back onto Zoom so that I can see if anybody's still there. I'll reattach my keyboard to my tablet. Here's some vague clapping.
Thank you very much, Matt, for this lovely talk.
Thank you.
Are there questions? Please, Pascal.
Yes. Thanks. Yes. Thanks so much, Matt. Could you go back to the definition of the rate function? So, well, of the action function, so for a given function f.
This thing?
Yeah. Okay. I mean, typically in these large deviation results, like because you want to have a quenched large deviation result, right? So then you would want the cost to be negative over all times, because otherwise, then the expectation of the number of particles following the trajectory up to a certain intermediate time point would be very small, right? So I mean, so for example, for the time inhomogeneous branching random walk, this is what you have to do. You have to truncate your paths that you're allowed to follow, because otherwise it would give the right order of the expectation of the number of particles, but not the actual number of particles. So
right, exactly.
Here, so maybe I didn't parse your formulas correctly, but it seems that you don't have this here, right? So
right, so this was, so K tilde is really the rate for the, like you say, for the expected number of particles. But if K tilde ever goes negative, then, so here on the next slide, we had K.
Oh, okay.
K is minus.
Okay. So I parsed it wrong. Okay, thanks. You had a question, please?
So thanks for the nice talk. Could you comment a bit more on how you control the early behavior of the model? Like, so maybe I think it's more or less the last page of your. Did you hear me or?
Yeah, I can hear you.
Okay. Yeah.
So, what this?
Exactly.
This page?
Maybe one page earlier. Yes, exactly. Oh.
Here.
Anyway, so I just want to ask, how did you prove that it's just really this particle that follows more or less this the line in the beginning?
At the beginning, yes. Yeah, so it is really tricky because because R is discontinuous, somehow a priori have no control over where particles are going. And if you have no control over where they're going, you have no control over over how fast they can split. But so actually we had to go to discrete time. We had to look at generations rather than, so if you sort of, I guess you could say it's stopping times, where the stopping times are the branching times of the system, then somehow the rates of branching are in this discrete time version are irrelevant, because you're just looking at the generation times. And then we could say, well, okay, everyone's branching at rate 1. So these branches, they're definitely everyone's branching at rate at least 1. So these things are happening at least at rate 1, and show that we could control, because there's always this drift into the lead diagonal. It was also the case that if what you don't want to happen is that particles just get further and further away from the lead diagonal, and somehow you can balance, because there's the drift in towards the lead diagonal, you can stop that from happening. So you can make sure there are enough particles staying within following near this lead diagonal up to a sort of very small time. And then if you want particles following, so if f primed of 0 is not, if f does not follow the lead diagonal, if f is following a different diagonal at time 0 in the phase plot, then you need to get these particles to follow the lead diagonal for a very small time, and then you get enough of those particles to feed whatever gradient f has at 0.
Which means that the rate of the, how to say, of the drift need to be strong enough so that like the particles are kind of being controlled in the region. It's being controlled so that it's kind of concentrate to the straight line. That's what you're trying to say, right? So
yeah, so we can control somehow at very early stages. We can control the rates well enough that we can at least get growth along the lead diagonal, and then we've got enough particles that we can introduce. We've got enough independence between those particles following the lead diagonal at very early times that we can get this feeding into other diagonals. And once you've got a few particles following that lead diagonal, again, once you've got a few particles going in the right direction at the start, then you can again control the rates along the path to get the growth that you want.
Thank you.
Bastien?
So thank you very much for your talk. So as you showed in your process, you have two effects that both are making squares more probable, right? You have this drift away from the boundaries and this extra branching when you're far away. Do you have an idea of which one is the more important one, or if you could just use one of the two? Like, for example, if you just branch fast enough, you create dust out of the thin rectangles and just get the square ones that remain.
Yes, so we don't get any. Well, yeah, I guess we don't get it. No, I don't know the answer.
So I wonder, you can understand using this distribution of the shapes of the rectangles at some time, but can you do something jointly for the shape in the location? So, for example, rectangles in one part of the square equal likely to be of any shape than rectangles in other parts of the square.
Yeah, yes, that's not something that we've looked at. It's definitely not accessible by the branching random walk picture, right? Because the spatial location of the rectangles is totally lost in the branching random walk. Yes, I'm not sure. Very, very good question.
No other questions. Then let's thank Matt again, and regards to your children, right? From all of us.